All right, everyone, welcome back. This is Mr. Fawcett, and we are about to start part 2 of the lesson regarding continuity over an interval. So in part 1, we took a look at this graph, answered some questions about whether the function was continuous over these different intervals, and then we drew our own graph. Given some constraints, we had to draw a function that matched those. Today we're going to do a discussion on classes of functions and trying to decide where certain functions are not going to be continuous. And again, we're going to talk more generally than specifically. So we want to kind of talk about an entire class of functions rather than just a single function out of that group. So we have 5 here to do. And again, once you kind of see what we're doing, for the first example, I would encourage you to pause the video and try to replicate that for the next class of function that's coming up, and then click play and hear the discussion. So we're going to start off with polynomials, and I'm going to give you 2 examples of polynomials, and then we're going to talk about some of the characteristics of polynomials. So we'll go with f of x is equal to 3x squared plus 5x minus 4, and we'll go with g of x is equal to negative 1.4 x to the power of 7 minus 2. So if we think back to what a polynomial is, it's a function that's a sum or difference of certain terms where the exponent on the variable is a non-negative integer. So we can't have negative exponents. We can't have fractional exponents. We can have an exponent of 0, and then we can have all the natural numbers being exponents. And those are our polynomials. So polynomials, and if you wanted to graph these and kind of look at their continuity, you would see that they're continuous everywhere. And that is a characteristic of the entire class of polynomial functions. They are continuous everywhere. Okay, so I know this one was a bit short. Take a look at rational functions. See if you can come up with 2 examples of rational functions, maybe ones that are slightly different from one another, and then think about where those functions may not be continuous on their domain. And then click play. Okay, so rational functions are essentially the quotient of 2 polynomials. So let's do pink here. So let's say I have an f of x function that's equal to 5 over x, and g of x will be equal to 3x squared minus 4 over, we will say, the quantity x plus 2 times the quantity x minus 5. So again, rational functions are just when you see a quotient where the numerator is a polynomial and the denominator is a polynomial. Think about where these functions are not going to be continuous. So where are they undefined? Well, when we see a fraction, we know that a fraction is going to be undefined when the denominator is equal to 0. So for any rational functions, we are going to look at what x values, or whatever inputs, make our denominators equal to 0. So for this function right here, it is continuous everywhere except x equals 0. And down here, continuous everywhere except x equals -2 and x equals positive 5. And it doesn't matter if we also get 0 in the numerator. So if we got something that was indeterminate, like 0 over 0, if we're taking the limit of a function and we get an indeterminate form, that means the limit can still exist. However, if we're looking for whether the function is defined at a certain point and we get an indeterminate form, well, because there's a 0 in the denominator, that function is not going to exist at that x value, regardless of whether it's just 0 in the denominator or 0 in the numerator as well. So for rational functions, we can sum this up as continuous everywhere except where denominator is equal to 0. All right, once you have that down, we're going to move down to functions involving radicals. Okay, moving on to radical functions, let's take a look at 2. So I'll have f of x is equal to the square root of x minus 5. And we'll do a different color here. G of x is equal to the cubed root of x minus 2. We'll do x plus 2. Why not? Okay. So if we think about radical functions and where they may or may not be continuous, we also have to think about where they may not be defined at all. So if we have a radical that has an index that's even, right? So I could, our index is right here, right? That's that number outside of the square root. We just don't write it for square roots because it's like the base case, right? So it's like not having to write 1 in front of x. We can just say x rather than 1x. For every other type of radical, though, we need to know what the index is because the operation is different than just a square root, right? A cubed root is a different process than finding a square root. 2 quick examples just to show us, right? The cubed root of 64, sorry, the square root of 64 is equal to 8. The cubed root of 64, well, that's going to be, what's a number that I can multiply by itself 3 times to get 64? And that's 4. Right, 4 times 4 times 4, 64. So that index tells us that we need to do something different based on what the value of it is. But essentially for even indexes, so a square root, a 4th root, a 6th root, an 8th root, etc., you cannot have a negative number under the radical, right? Otherwise, we're going to get into the realm of complex numbers, which is not something that we deal with in calculus. We only work within the real numbers, not the complex or the imaginary. So this purple function right here, f of x, is only defined for x values that make x minus 5 greater than or equal to 0. So essentially, this is continuous. Let me get out the pencil. It is continuous on the interval 5 to infinity. Okay, if I substitute any number in between 5 and infinity, not only is the function going to be defined, but it's going to be continuous at that point. The same, it's slightly different when we have an odd index. So for the odd indexes, 3, 5, 7, 9, 11, etc., we can have something negative under the radical sign. A quick example, right? If I take the cubed root of -8, right? Well, there's a number, when I multiply by itself 3 times, it gives me -8. It's -2, right? -2 times -2 times -2 gives me -8. But there's no number, right, that's going to be the answer to this expression unless I start to use imaginary numbers. So this has no real answers, whereas this right here does have an acceptable answer, -2. And again, it's based on what that index is telling us to do. So when we have an odd number in the index, we don't have to restrict our domain at all, right? This function right here is continuous on the interval -∞ to infinity. I can substitute in any number, any real number I want, and I'm going to get the function's going to be defined, and it's going to be continuous. Okay, so the only work you have to do is when you have indexes that are even, you have to figure out what numbers are going to make the expression under the radical positive, and those are going to be what your domain consists of. Okay, let's sum this up a little bit. So we will say radical functions are continuous. Continuous when expression under the radical sign is non-negative. So it can be equal to 0. It just can't be less than 0. It just cannot be negative. And then remember, this is only applies to even indexes. Radical functions with odd indexes are continuous everywhere. Okay. We are now going to move on to exponential functions. All right, so exponential functions actually are quite nice because their continuity is similar to polynomial functions. Let me give you two examples of exponential functions. We'll do f of x is equal to 2 to the power of x, and we'll do g of x is equal to 1 over, let's do e to the x minus 3. So just thinking about the continuity of the pink function, is there any place where the function's undefined? And you could test some numbers or think about what the graphs of exponential functions look like, but there are no places where this exponential function is undefined, and it's also going to be continuous everywhere. So and again, I'm writing continuous everywhere. Again, we are speaking for all real numbers. If you wanted to write the domain or for where the function's continuous from -∞ to infinity. The blue function looks a little different. We do have this fraction here, and you may think, okay, well, what if this fraction ends up with a 0 in the denominator? Wouldn't that make the function undefined? Well, you'd be correct, because we can't have 0 in a denominator. However, e to the x never will have a value of 0. If you think of what the graph e to the x looks like, it looks something like this. Right? Its y-intercept is 1, and it has a horizontal asymptote on the x-axis. So it approaches y equals 0, but it never actually gets there. It never actually touches it. So this function as well is continuous everywhere. Or if you want to write it in interval notation, we have negative infinity to infinity. So your first thought may be, okay, well, I guess all exponential functions are continuous everywhere. And you're 99.9% correct. The only exception is when we have 0. The only exception is when we have something that would be 0 to the power of 0. That's going to be undefined. We're not going to get into why it is right now, but this is the only time where an exponential expression is undefined, when it's 0 for the base and 0 for the exponent. So exponential functions are continuous for all real numbers, or you could say continuous everywhere. Except for 0 to the power of 0. Okay, but in general, for all intents and purposes, exponential functions are continuous everywhere. All right, let's move on to our last section, composite functions. All right, so let's say I have f of x is equal to x plus 3, and g of x is equal to 1 over x. And the composite function that I'm going to come up with is h of x is equal to f of g of x. So our question is, where is h of x continuous, or is h of x ever not continuous? Well, if we think about what h of x is going to look like, h of x, we are going to replace, this is now our input for f, right? The entire g of x function is our input for the f of x function. So we end up getting 1 over x plus 3. And this function would be continuous everywhere except, hopefully you know which value I'm going to talk about, x is equal to 0. Now if you wanted to write this in interval notation, we would write it like that. And we can talk more about this little U-shaped symbol. It just means that we're combining those two intervals in our answer. So we're including the negative infinity to 0 and the 0 to positive infinity. So in general, for composite functions, the resultant function, this h of x function, will be continuous when both g of x and f of x are continuous. So composite function is continuous when the functions it is built from are continuous. Right, so not only does g of x have to be continuous, but f of x does as well. Okay, hopefully this was a good refresher about the different classes of functions, some of their characteristics, and where they are continuous, where they're not continuous. We're going to come back for part 3 of this video and come up with a definition for a function being continuous over an entire interval. So now we've just kind of been exploring. In the next video, we are going to actually look at what that hard definition looks like. All right, until then, this is Mr. Fawcett. Enjoy the rest of your day.